This is Unit 7, Video 9. In this unit, or in this video, we will talk about thermochemistry. And thermo essentially refers to heat, and we will connect heat now to chemical reactions. We've talked about heat, absorbing, releasing heat, and physical changes. Now we're going to talk about the same thing with chemical changes. Every chemical reaction, remember, has an energy change associated with it by definition. So we'll take a look at these in this portion of the chapter. First, let's define or discuss the difference between heat and temperature. Now, a lot of people think that heat and temperature are referring to the same thing, but they are not. Now, just to kind of show you the difference, here I have a block of aluminum, and here I have a block of water. We'll say it's the same mass of aluminum, same mass of water. If I apply a certain amount of heat, say 10 kilojoules of heat to both the aluminum and 10 kilojoules of heat to the water, will they go up by the same temperature? And the answer is no. And we've seen this because they have different specific heats. They will rise in temperature by a different amount. Aluminum will rise in temperature higher than will the water. So obviously the heat here is the same, but the temperature is not. So we know heat and temperature are not the same idea. Heat, here it says, is defined as the total amount of energy in an object, whereas temperature is the average energy in that object, the measure of the average energy in the object. So a good example to show you the difference between this is a question like this. Here you have an iceberg, a nice and big iceberg, and here you have a boiling pot of water. So the iceberg is probably below 0 Celsius since the ocean is actually salty, but we'll say the iceberg is maybe -5 Celsius or something. We'll say it's a warm northern Alaskan day here, and we'll say this is 100 degrees Celsius. Okay, which of these objects have more energy? Well, or more heat, I should say more heat. Which has more heat? Why don't we say it that way, energy or heat in this case? And the answer is the iceberg actually has more heat. Why? Because there are so many more molecules in the iceberg. Each molecule has less heat than each molecule in the pot of water, but there is such a bigger amount of molecules in the iceberg that the total heat is actually more total heat in the iceberg, if that makes sense. So heat is actually different than temperature. The temperatures here are different, definitely different, but the amount of heat contained in the iceberg is greater than the amount of heat contained in the pot of boiling water. If you extend this amount of energy over the whole iceberg, it'll be insignificant, you can say. It won't do anything, it won't raise the temperature of the iceberg really by much. And that's the idea. So hopefully you see the difference between heat and temperature. Now energy is defined as the ability to do work or transfer heat. So it's actually connected to this business of heat. So there are two ways you can work with energy, or there are two ways you can calculate energy. One of them is to focus on work. So here it says energy to cause an object that has a mass to move is called work. So anytime you're doing work, if you're pushing something, pushing a desk, you are actually putting energy into the system. And there's an equation for it, and the work is force times distance. You can actually determine how much energy there is from doing some sort of amount of work. And then energy is also used to cause the temperature of an object to rise, and that we'll call heat. So these two definitions usually go into the idea of energy. It's work and heat. Now we're going to be talking a lot about heat in this video and the next. We're not going to be talking too much about work. But the unit of energy, which you've seen already, is the joule, or rather the SI, the international agreed upon unit of energy is the joule. But there is an older unit called the calorie, and this is still used in nutrition and so forth. So a calorie is defined as 4.184 joules. And we saw that this is actually the amount of heat it takes to raise the temperature of 1 gram of water by 1 Celsius. And that was the definition. This is actually the specific heat of water at some temperature. In nutrition, the calorie is actually that's used as a capital C. What that means is they're actually referring to kilocalories. So 1,000 calories, regular calories, is 1 kilocalorie. That makes sense because kilo means 1,000. But the big case C calorie is actually a kilocalorie. So on nutrition labels, if something has 12, if it says it has 12 calories, it actually has 12,000 little calories. And if you divide that by 4.184, you'll get somewhere in the range of a little less than 3,000 joules, which is quite a bit of energy. So hopefully that makes sense. So this is what we define as energy. All right, there is something called potential energy and something called kinetic energy. This is a study of energy from just the theoretical perspective. It applies to both physics and chemistry, and we're going to apply it to chemistry in a minute. So potential energy is, you think of this as the stored energy, and it's the energy an object possesses because of its position. So in the case of physics, if something's higher up, it has more potential energy than if something's lower, compared to another object. Kinetic energy then is the energy of motion. The energy an object possesses because of its movement, its motion. And you can convert from potential to kinetic energy. So here, for example, the cyclist is converting the potential energy she has at the top of the hill into kinetic energy. She doesn't have to pedal, it just kind of goes down. And the same thing applies to chemical reactions. Anytime you have a set of molecules, say a set of hydrogen molecules and a set of oxygen molecules, this system actually contains some potential energy. It's like being at the top of the hill. When you react them, then these molecules form water. And a lot of heat is released. A lot of kinetic energy is created, essentially. So heat here is released from the system. So this same idea can actually apply to a chemical reaction, and that's what we're going to do in this unit. So we have to define something called the system and the surroundings to kind of talk about this in a little more detail. The system then would be your chemicals, your molecules that are going to react. In this case, I have the same example. Here are oxygen and hydrogen. These are hydrogen, these are oxygen. The red are the oxygen. So that's the system, the chemical reaction. The surroundings then is everything around the system. Now this includes the cylinder. It even includes the space around the cylinder. It includes, if there was a water, if this was a solution, then it would include that water. So everything that's around those molecules. And those molecules are going to release the energy to the surroundings. And that's kind of the idea. And because of the first law of thermodynamics, which says energy cannot be created or destroyed, it can only be transferred, the total energy of the system, or of the universe, here it says is constant. So if the system loses the energy, that energy must be gained by the surroundings. So the idea here is the whole reaction total, the whole system total, should be transferred. The energy from the system should be transferred to the surroundings because the universe has the same amount of energy before and after the reaction. Hopefully that makes sense. So if we define the change of energy as the delta E, this delta business in science, it means the change of, what we could say is that this is always final minus initial. So if you're changing an energy, it's the final energy of the system minus the initial energy of the system that gives you the delta E. So for example, if you began with an energy of 15 kilojoules, and then at the end you end up with an energy of 10 kilojoules, well, you've released 5 kilojoules of energy. Your final state, in this case, is actually going to be 10 kilojoules. Your initial is going to be 15 kilojoules. When you subtract the two, what you'll see is you'll actually get negative 5 kilojoules. And you'll see that this negative will actually indicate a release of energy. That negative sign will show you that energy is released. And this is how we define a change in energy. Good? So now we're going to define something called enthalpy, which deals with heat, which is actually the heat portion of the energy change. And because we're not going to do too much work, or we're going to do some work, but we're not going to calculate the amount of work created by chemical reactions. There is work created by some chemical reactions, especially if it's a gaseous type reaction. You'll have some work possibly created, but we're going to essentially ignore that, and we're going to only look at the heat portion of a chemical reaction, partly because the heat portion of a chemical reaction is much greater than the work portion, and then partly because all of chemical reactions have a heat change, but only those involving gases have a work change. So we're going to focus more on heat. And the heat, using a fancy word, is called enthalpy. So for that we use a delta H or an H. H kind of matches heat. And we will call this business delta H. So from now on we'll actually stop talking about delta H and not about delta E. Again, delta E considers both work and heat. So now what we're going to do is we're going to not worry about work, but only talk about heat. So we will talk about the change in the heat of the system, the heat energy of the system. Hopefully that makes sense. Alright, so here's an example. The enthalpy, or the heat change of a reaction, is defined as the products minus the reactants, just like before, just like with energy. So if you have 15 for the products and 20 for the reactants, you have 15 minus 20 and you get negative 5, kind of like we've seen before. And in this case, what you have up here, you have your reactants. This is CH4, a hydrocarbon, plus oxygen. And what will happen is that will be a combustion reaction that produces CO2 and H2O down here. Now you'll notice that the CO2 and H2O are at a lower energy state, and these are at a higher, the reactants are at a higher energy state. This is like the potential energy. These guys up here have more potential energy, and then the products have less potential energy, so that energy was released. How much energy? Well, in this case, it's negative 880 kilojoules. That negative actually means the fact that it was released. Whereas here, the positive, going up the other way, would mean absorbed. You can actually reverse a reaction and look at it from both sides. So we'll call this the enthalpy of reaction, or sometimes the heat of reaction. Sometimes what they'll do is they'll do delta H, and they'll put reaction down here. So this means the heat, the change in heat of the reaction. And again, it could either be positive or negative, depending which way it's going. When heat is absorbed by the reaction, delta H will be positive. This is called an endothermic process. You've heard of this term before. And endothermic means positive in the terms of heat change. When heat is released, delta H is negative. So another way of showing this, here we have the system, the chemical reaction itself, and it's releasing heat to the surroundings. Notice heat is coming out of the system. So if before we had 15 kilojoules, and after we have 10 kilojoules, then if we do final minus initial, we'll do 10 minus 15, and you get negative 5. So that's how you're negative if you are releasing heat, exothermic. Another way of saying this is delta H is less than 0. So in this case right here, delta H being less than 0 means delta H is negative. That's the same thing as saying it's an exothermic process. So really you can say three things. You can say delta H is negative, you can say delta H is less than 0, or you can say exothermic. All three of these are actually saying that the system is releasing heat, the reaction is releasing heat. And then the opposite is true for an endothermic process. So you can actually do the same calculation. If you began with 15 and ended up with 20, that means if you do final minus initial, you do 20 minus 15, you get positive 5 kilojoules. And so you can say that delta H is greater than 0. That's the same thing as saying delta H is positive. You can also say it is endothermic. All those refer to the fact that the system absorbs energy. Now, most of the time, the system by itself will release energy, but there are reactions where it does absorb energy. Okay, so here's how we write this heat change in a chemical reaction. You have your standard chemical reaction, in this case hydrogen plus oxygen to give you water. And then if it is producing heat, if one of the products is heat, which means it is releasing heat, you can actually put the product, a second product, as the heat. You can say plus it's forming 2 moles of water, plus it's forming 483.6 kilojoules of heat. But more commonly what we do is at the end of a reaction, we'll write delta H equals that much heat. And you notice here the negative. This negative actually shows you that it is released. That's the idea. Heat is released if it's negative. That's why we need a sign, so that way we can tell if it is absorbed or released. And delta H, this number here, says it's per moles of balanced equation. So if you form 2 moles of water, you're releasing 483.6 kilojoules. If you form 4 moles of water, then this number will be double. So in other words, this is connected to the balancing of the equation, and that is always the case. So this is actually usually per mole. This is referring to per mole of the reaction. actually do some example problems and show you how this is done. So here we have a reaction, the same one we've seen up above, that releases 890 kilojoules of heat. Notice it's releasing 890 kilojoules. So how much heat is released when 4.5 grams of water is formed in this reaction? So this will involve some stoichiometry. Stoichiometry never hurt nobody. So let's go ahead and try it here. What we'll do is begin with the 4.50 grams. This is 4.50 grams, in this case of water, of H2O. Now notice what we're asked is to convert essentially from grams of water, from here, to heat, to here. So it's really a conversion from grams of water to delta H. Now we're going to go from grams of water to moles of water, and because the connection is 2 moles of water produce this much heat, then we're going to convert from moles to heat. That's the connecting unit. So this will actually be grams to moles, then moles to heat. It's a 3-step equation involving heat. So this will be 3-step, 1, 2, and 3. So we're first going to go from grams of water to moles of water. Then we'll go from moles of water. Oh, this is actually a 2-step, apologize. We can go from moles of water to kilojoules. Not a 3-step, just a 2-step. Unless we're asked to do joules or something. That 2-step. There it is. Make it easier. Alright? So now you'll see that the connection here is from moles of water to kilojoules. And again, it's 2 moles of water, based on the balanced equation, for 890 kilojoules. Now, you could put the negative if you'd like, and then your heat change will come out as negative since it's being released. In this case, a mole of water is still 18.02 grams of water. Go ahead and let's do this calculation. Pull up your calculator. We got 4.5 times 1 divided by 1802 times negative 890, and you get yourself 222. It's a nice number. Let's see, since we have 2 sig figs, because we're really limited by our delta H, we've got 220, negative 220 kilojoules. So when you form 4.5 grams of water, you will be releasing 220 kilojoules of heat. That's how it works. So pretty simple, hopefully, not too difficult. Let's do another one that goes backwards. Here we have a reaction that is endothermic. Now, you've got magnesium oxide, which is broken apart, decomposed into the original magnesium and the original oxygen. In this case, it's a positive 1204. So you have to put energy in because we're breaking bonds here. That's what you're seeing. And it goes backwards. It says how many grams of magnesium are produced when 325 kilojoules of heat are used in the reaction. So we're going to go from heat to moles of magnesium, and then from moles of magnesium to grams of magnesium. So that should be very similar to the last problem, except backwards. 2 steps, not 3 steps, 2 steps. So let's begin with our heat, 325 kilojoules. And then we're going to convert from kilojoules into moles of magnesium. And then we'll go from moles of magnesium into grams of magnesium. Again, the relationship here is 1204. In this case, it's positive. Kilojoules of heat for 2 moles of magnesium. And then the molar mass of magnesium is 2431. So simply take a look at the periodic table for that. All right, so the problem is just as simple as the previous one. 325 times 2 divided by 1204 times 2431 gives you 13.12. Now we have 3 sig figs rather. So how about 13.1 grams of magnesium? So when you put this much heat into the reaction, you'll produce 13.1 grams of magnesium. Hopefully that made sense, and we will resume in video 10.